So we're now going to discuss briefly how non-integer real numbers are represented in a computer. And the problem is that they cannot be represented exactly because you need to make cutoffs. Well, not all of them can be represented exactly. Some can, in fact, and it's important to know which ones. So first, I'm going to give a sloppy description of how they are stored, and then I'm going to give a more accurate description. I cannot give the most accurate description because, well, this changes a lot, and there are a lot of small details that engineers have put into this. So while the way computers store integers is fairly straightforward, the way they store non-integers is complicated. But now we're just going to try to get enough understanding to know when round-off errors occur, because they can be important sometimes. So the sloppy description is as follows. So let's, as an example, start with the square root of 2, which is 1.4 and so forth. How is he stored in a computer? Well, the computer now does two things. So if we're in a 64-bit computer, remember it uses a sequence of zeros and ones, so 0, 1, 1, 0, 1, whatever. And here you have 64 bits, okay? And he stores this number here on the form alpha times 10 to the beta, where here for the alpha, which is sometimes called the fraction, which doesn't really make sense now that we are doing this sloppy description. But this thing here is a 16-digit integer, and this beta here is roughly between, it's an integer between -324 and 308, roughly. We're going, at the end of this film, we're going to talk about a more exact description. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I mean, we have an infinite number of digits here, but these apparently are the first 16. This means that here we're getting a break, so all of this is lost. Okay, this the computer will just throw away. So the alpha here will be 1, 4, 1, 4, etc. like this. I hope I got it correctly. And notice here, there is no comma here, okay? So this alpha here has no comma, and that's the job of this guy, to place the comma. And for this reason, the method of storing non-integer real numbers in a computer is called a floating point number. Basically means you store a 16-digit number and then where the point is supposed to be. So then, of course, this is a huge number. So this is 10 to the 16 something, and we want to put the comma here. So to make this happen, I should put beta here rather. We need to put beta to be equal to -15. So -1 would put the comma here, -2, -3, -4, -5, -6, -7, -8, -9, -10, -11, -12, -13, -14, -15. So with these choices of alpha and beta, this part of this guy will be on the form alpha times 10 to the beta. But notice, no equality here. So let's now talk about the more accurate description of how a floating point number is really stored in Python. So first of all, we need to recall that, okay, so this is stored as a string of zeros and ones, okay? So each of these represents a bit, and all in all, we have 64 bits here, okay? And we now group these together in specific ways to represent the floating point number, okay? Some of this will be this 16-digit thing, and some of this will be this exponent. So how does that work? As with integers, this one here is just the sign. And now we'll have 52 guys here for alpha, which would just now make it a 52-bit integer. And then here we have how many bits are left? 11, I think. So 11 bits for exponent. And now these 52 bits, so we don't call this, this is not an integer using these two complements, because now the alpha here, just a string of bits, is going to be put after a 1. So you kind of, in order to get a little bit extra, you say that, well, every floating point number is 1 comma and then this alpha, and then this is to be interpreted. So just put a string of zeros and ones here, and this is to be interpreted as a binary number. And then you multiply this by 2 to the power beta. So this is an integer using this 2's complement stuff. And then you can try to figure out, okay, what's the smallest beta? What's the largest beta? And roughly what powers of 10 do you get from this? And then you can look here. So what's the you can say the biggest and the smallest numbers I get here, or rather how long are these when you convert them to decimal notation? And you'll see that this here will give you numbers that are roughly or up to 16 digits long in the base 10 number system. And there's one important thing to notice here, is that when this beta here is the smallest possible, so this 11-bit integer here is minus the largest thing it can be, then this 1 here is converted to a 0. So then this is to be interpreted as 0.alpha2, like this. This allows us to get a better accuracy. So it gives us, for free, some smaller numbers. So this all is perhaps a bit abstract. So let's do an example where we look at how 1/10 is stored in a 16-bit computer. And I do 16-bit here because I don't want to deal with 64 bits. And in a 16-bit computer, so you have a string of 16 zeros and ones, and out of these, so we have one sign here, and then the remainder are split between the alpha and the beta. And the exponent is 5 bits, and how many do I have left? I have 10 here then, 10 bits for alpha. So this means that the alpha here is a string of 10 zeros and ones. So first of all, what you want to do is express this on binary form, okay? So that's a type of math that we really don't get into here, but it's not terribly complicated. But in this case, it will be 0.00011001100110011 and so forth, 0011 continuing forever. So I have to start here and then taking the first sequence of 10 non-zero guys here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this will be my alpha, which means that 1, alpha 2 is 1, 1100110011. What do we do next? Well, the first one I always get for free, well, unless the beta is the largest and most negative it can be, which means we're looking at really, really small numbers. This is not the case here. So here I get the first one for free. So I get him for free. And then I'm taking the next 10 guys here. So how many are those? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like this. So 1, alpha 2 would then be 1, and then 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. And of course, this 0 doesn't really matter. And this is a binary number. And then my beta. So when you multiply by 2 to the beta in binary, you're just moving this digit or this decimal point here. So this is how my number looks. So I need to move my decimal point. It's here in the representation so far. So I need to move it 1, 2, 3, 4 spaces to that side. So I need to do here 2 to the minus 4. So yeah, this of course isn't equal. So now we have that this thing here approximates. And notice here, this is quite shocking. Since 1/10 does not have a finite expansion in base 2, this means that we have to do a cutoff, which means that 1 to the 10th cannot be represented accurately in a computer, which means that whenever you put 1 to the 10 inside of a program, you will make an error. And that's a bit shocking because this, to us in the decimal world, is really one of the simplest fractions. But for a computer who lives in a binary world, this fraction is no easier than 1 divided by 3 is to us. And of course, 1 divided by 3 would be a really simple fraction in a world where people counted with 3 fingers. So who are the simple fractions or the easy fractions that changes when the base number changes? So what number is this? Well, if we want to convert back to decimal, that's not so difficult. So this is 1 times 2 to the 0 plus, and this is 1 times 2 to the minus 1, 0 times 2 to the minus 2, 0 times 2 to the minus 3. Then we have 2 to the minus 4 and 5, and then not 6, not 7, but 8 and 9. And then I multiply all of this by 2 to the minus 4. And then you can see what this becomes. Well, this becomes 1 plus a half plus 1/16 plus 1/32, 1/256 plus 1/512 times 2 to the minus 4, and 2 to the minus 4 was 1/16. And all of this is equal to, and if you go to Google to check what this is, this will give you 0.09997. You're missing by 1/50,000, basically, in a 16-bit computer. I can end this by saying that to check the accuracy of your computer, you can check how small do you have to take a number epsilon for the computer to think that 1 plus epsilon is equal to 1. The largest epsilon that fools the computer in this way is called the machine epsilon. And the machine epsilon is relative to size. So for 10, the epsilon would be 10 times larger. So it's really, you have to do it for 1 here to get the machine epsilon. But also note that if I take a number a sufficiently small, then Python will think a is equal to 0, even if it isn't equal to 0. Now, the number a for which this happens will be much, much, much smaller than the machine epsilon. And if you think about how floating point numbers are stored using the sloppy description, you can understand why the machine epsilon is much bigger than the smallest non-zero floating point number. So that's a good exercise to reflect on that.